Hey, welcome back. Last week we saw music visualization. This is what it looked like. In episode 46, we saw particle deflection. It looked like this. Whenever I move my mouse, the particles are sort of deflected, and when the mouse moves away, they sort of fall back slowly into their original positions. Now, I just realized that I could use this particle deflection or the placement of these particles to create something like a dithered image. And that dithered image can be used to create music visualization. So let's do that. Alright, let's talk about dithering for just a little bit. You've probably already seen dithering without realizing that that's the technique that is being used to print such an image. In a lot of print media, including newspapers, even today, any image that you see or any photograph that you see probably uses the dithering technique to sort of print these images. Here's an example of an image of Bill Clinton, and if you zoom in or if you look very closely, you will see that this is the pattern that is being used. So what is happening over here is that the grayscale image is created by shrinking or by growing the size of the black dots, that is being shown. So that gives an illusion of depth, and this is the technique that they use as little ink as possible to print this image. Here is another technique where the density of the white dots is being used to basically give an illusion of depth to an image. So dithering is a technique by which you can create images like this. In this episode, we are going to be applying dithering to images. There are many algorithms that will do this for you, but we will use a very simplistic model to do it. Now, to do this, we must first understand how images and pixel data work in JavaScript. So let's see that for just a bit. When an image is converted to pixel data in JavaScript, it appears as an array of integers that looks like this. Each pixel is represented by 4 elements of this array. The 4 elements are the red, green, blue, and alpha or transparency of the pixel. So yes, the pixel data of the image will be 4 times the size of the image. The total size of this array would therefore be width into height into 4. So let's look at just 2 pixels of this image and see what their RGB elements look like. Take this black pixel for example. Its RGB value will be in the lower range of 255 because it's black. Remember, 0 is the lowest and 255 is the brightest. But if I look at this blue pixel, the RGBA value would look like this. As you can see, the blue value is the highest. Remember that the alpha would always be 255 because all of these pixels are completely opaque. The technique I will use is to find the maximum of the red, green, and blue components. Check if they exceed a particular threshold, I'll just say arbitrarily 125. And if they do, I'll convert this pixel to a point. So my hope is that when I apply this technique over and over again to all of the pixels of the image, this is what I'll end up with, where I have all of the pixels of the image represented as points. And these points can actually be, let's say, drawn on a canvas. So for the first technique, let's convert our pixels into points and we'll go from there. Let's create a function called loadImage. It creates an image and assigns the bigint logo.png to the source attribute. When the image has finished loading, we'll fetch the size of the image by using the width and the height properties. I'm creating a variable here called factor, and this factor is actually the width of the canvas divided by the width of the image. So the intent I have over here is that the image would be smaller than the canvas. It needs to be smaller than the canvas so that the dithering can happen in a more natural way. Next, we will draw this image onto a temporary canvas. We'll convert the canvas into a series of pixels using the getImageData function, and those pixels are actually stored in a variable called the pixel data variable. We'll traverse through this pixel data and we'll create a variable over here called current pixel, which can be calculated like this, which it is basically the I plus j into the image width into the number into 4, because remember, every pixel has 4 integers associated with it. Now once that is done, all I have to do now is get the red, green and blue values from the pixel data. Alright, so that can be fetched like this. And once that is done, what I'm doing here is I'm creating a variable here called max, and that would be the maximum of the red, green and blue values. Now, if this maximum exceeds a specific threshold, then I'm calculating the X and Y location of where this point should be on the canvas. That's very easy to calculate because remember, we have calculated the factor beforehand. So I have the factor and that would become the X and Y. I create a new point and I push it onto a points array. And once that is done, all I have to do is set the image data back onto the context. With that being done, let's also render this on our canvas and see how that goes. We'll create a function called dither that will be responsible for drawing all of the points on the canvas. We will start with, of course, erasing everything off of the canvas. And what we'll do is we'll set a specific fill style, and for every point that is there in the points array, we will simply draw a very small rectangle onto the screen. And then of course, we are going to be looping this dither function by calling the request animation frame. With that being done, let's look at what we have created. This is what the result looks like. So the image has been converted into a bunch of points, and those points are actually rendered on the screen as we intended. Now it looks too neat, too ordered. So I'm just going to introduce a little bit of randomness into this dithering process. And the way to do that is, is over here when we create the point. I'm just going to create a bunch of variables, a couple of variables called random x and random y, which are a random value between -1 and 1. And I'll just simply add them to the x and the y points. So if I say and rand y, and if I now refresh, start visualization, you can see that the dithering is a little bit more randomized. Now you can of course adjust the randomness with which the points would be offset by just a little bit. All right. The other thing that I want to do is to ensure that the red, green and blue values are all not always considered. And the way to do that is I can say only consider the red part of the image. So if I want to do that, what I'll do is I'll just say let green is equal to 0, so that I don't consider the green part of the image itself. And I'll comment this one, and over this also I'll just say let P is equal to 0, so that we only consider the red part of it. So we have not considered the red and the green parts. I'm sorry, the blue and the green parts of it. We are only considering the red part of it. And if I now refresh, and if I say start visualization, the dots would still appear, but they are not as dense as they were. All right. So this sort of reduces the number of points that are there on the screen itself. Now there is a reason to that, but because what I want to do right now is I want to sort of start displacing these elements, these points that are there on the screen, and we'll see how that goes. In our dither function, we'll first get the distance between the particle or point and the mouse. If this distance is less than a threshold that we have pre-declared, then we'll calculate the angle between the mouse and the point. We'll calculate the opposite angle of this by simply reducing math.pi from the angle. We'll calculate the new x and y locations using the cos and sine functions from the current mouse location. Next, if the particle is away from its anchor point, then we'll simply get how far away this anchor is and calculate the speed. We'll normalize the speed, and this is a fancy way of saying that we have converted our speed to a value that is either 1 or less than 1. The speed with which the particle must return to its anchor point is calculated and then added to the x and y locations of the particle. If the distance to the anchor point is within a certain snap distance threshold, then we'll simply snap the particle back to its anchor point. So one of the changes I made was that I changed this fill style to RGBA, and I have reduced the alpha part of the RGB, all right, so that the background erasure happens slower. Let's look at what that did. Now when I refresh the screen, I'll say start visualization, and you can now see that the particles actually do get back to their original anchor locations, and the alpha part of the fill style also does its part in actually making this more beautiful. Now what I want to do is tie in the music playing part of last week's episode to this image in such a way that when the music is playing, remember we get something called as the data array. Now I want to pick random elements from this points array that we have and sort of have them dance on the screen. I'll code that up and we'll see what the results look like. Remember, when the music plays, we get the music frequency in an array called data array. We'll get the frequency data from this array and reduce it so that it is more manageable. We'll get a random point from our points data and simply set its X and Y location to a random point within the frequency range. Let's see what that did. I'll start the visualization and also start the music. The mouse also works, obviously. I can do the mouse thing as well. Look at what happens to the overall image when the beat starts playing, when the major beat starts playing, right? The whole image sort of looks like it's responding to the music. It creates a very beautiful effect. So that's all I had for this week. This week was coding, but the next week is podcast because it's the end of the month. Ravi has challenged me to a debate. Now, I don't know if you know this or not, but I'm sort of an EV enthusiast, and Ravi absolutely hates EVs to the core. He thinks all people who go for this EV and all of the, he's sitting right opposite to me, by the way. Anyways, he thinks all people who buy EVs are fools and idiots, and they cause more damage to the environment than, right, Ravi?
Somewhat.
All right. So do join us again next week and let's debate this out. He says he has some plans to trap me, or he has some debate points that can trap me. I don't think that I can be so easily fooled. We'll see how it goes next week. See you. Bye.